For this section of high performance computing, we will only cover the surface level of a few of the related topics. The first one is pipelining. If you really understand about the fetch execute cycle, you will realize that there is no need to wait for one instruction to complete the entire cycle before we begin with the next one. For example, this is the cycle. Start with fetch, decode, operand fetch, and then execute. Let's say if we have two instructions to be executed, we fetch the first instruction and then we decode it. While we are decoding the first instruction, we can straightaway fetch the second one. The second one doesn't have to wait for the first instruction to finish the whole cycle first. That is the meaning of pipelining. Definition: pipelining is an enhancement to the fetch execute cycle where the subsequent instruction can start a stage in the cycle while the previous instruction is at the next stage without waiting for that instruction to finish the entire cycle. For example, let's say we have a few instructions to be executed like this. Let's say the first instruction is add cc, followed by load, srl, subcc, and so on. And the columns here indicates the value of time, and the row indicates the stages in the fetch execute cycle. So at time equal to 1, we fetch the first instruction. At time equal to 2, the first instruction that was fetched just now is being decoded. The second instruction can be fetched without waiting for the first instruction to finish the whole thing. While it is being decoded, we can fetch the second instruction. And at time equal to 3, the second instruction just now is now being decoded, and the first one is to be fetched the operand. At that time, the third instruction is already being fetched. The same for the instruction number 4. When time equal to 4, it is being fetched while the third one being decoded, and so on. This is what happens when we do pipelining enhancement to the cycle. However, there is a catch for this kind of improvement. Obviously, pipelining can be smoothly done if the sequence of the instruction are properly synchronized and do not depend on the result of the earlier ones before they complete the cycle. This logic to automatically rearrange the instructions so that pipelining is at its optimum level is done by the compiler, or actually is done by the assembler. Sometimes to force synchronization, we need to force delay so that the earlier instruction has to finish certain number of stages before the next instruction is being executed at certain stage. For example, we have a set of instruction that some doesn't depend on any other instruction, some depends on some other instruction. For example, this SRL instruction is using register 3 and register 5, and none of the other instruction is using that two particular registers. However, this load instruction and subcc instruction, they depend on each other because load is using register 2, subcc also using register 2. Subcc is actually overriding the content of register 4 somehow into register 2. If this is done too early, the load instruction in this stage will be loading a wrong value from register 2 to register 1. So we have to put a delay, a no operation instruction here. But knowing that this instruction does not depend on any other instruction, we can sort of replace this no operation with this one, becoming like this. This logic, rearrangement and putting delay is done by the assembler or the compiler. Next topic on high performance computing is about register overlapping use. This is a further improvement on pipelining. If we have a microprocessor that have a large number of registers, that the processor can consider registers like memory location, which means the registers can be considered some to become input register, some can become the output register for certain procedural call. So the definition, overlapping register use is the use of input registers by a second procedural call while the first one has not yet written or has not yet finished, but it already finished using the input registers, which means the input registers which were belonging to the first call now can be used by the second call even though the first call has not finished yet. Example, let's say this is the point of the execution where procedure A was called, and these are the set of the register that was used by procedure A to become input register, register 8 to register 15. And at this point, the call to procedure A completed. But at the point of register 16, procedure A already finished using the input register. So after this point, the next call to another procedure, for example, procedure B, which is called at this point, can already use register 8 to 15 as input, even though the procedure A is not finished yet, but it already finished using register 8 to 15. So procedure B can use the same set of register, even though procedure A is not finished yet, because the execution is overlapped, but the actual value that is used is not overlapping, because we have to make sure that procedure A is already finished using the input. Now register B can use the input registers. So this is the enhancement that we can get by having registers to be overlapping used. The last topic on high performance computing is about low power coding. Low power coding has attracted a lot of attention in the contemporary micro P design because we need more microprocessor to be able to run mobile devices that rely on battery. There are many ways to make microprocessor use less current, but for our topic in computer organization and architecture, we shall consider this in designing the instruction set. Let us consider these 4 lines of load assembly instruction. The 4 load instructions are totally independent of each other. They are all using different registers and different memory location. And let's say this is how the manufacturer of the microprocessor map the machine code from the assembly code. For example, the registers 16, 17, 18, and 19 is encoded in these 5 bits, 16, 17, 18, and 19. And this memory location is encoded in the last almost half bits of the machine code over here. And we don't have to care about the meaning of the other part of the bits in the machine code for this discussion. This is the machine code, and it is given in this sequence. From the first instruction to the second one, we can see there is one bit change at this bit and another one at this bit. So from first instruction to second one, we see 2 bit changes. And from the second one to the third one, we see this one bit change. This bit also change. This is another bit change. And this is the fourth one. So we see 4 bit change from instruction 2 to 3. And from instruction 3 to 4, we see this bit change, this bit change. So there are only 2 bit change. This is a typo. It's supposed to be only 2 bit change. So the total bit change is 8. 2 plus 4 plus 2. The total is 8. But this total number of 8 bit changes can be reduced to 6 only if we rearrange them. Remember the 4 load instructions just now, they are all independent from each other. We just swap the last 2 instructions. Instead of having it register 16, 17, 18, and 19, we swap, we do the one involving register 19 first and then 18. You can see there's no change here because we didn't swap. 1 bit change, 2 bit change from instruction 1 to 2. But from instruction 2 to 3, now we see only 1, 2 bit change. So this is where we get the reduction of 2 bit changes. And from instruction 3 to instruction 4, the same bit change because the pair of the swap instructions will still have the same number of bit change. 1 and 2. So now the total number of bit changes are only 6. 2, 2, 2. With less transition in the machine code, there will be less power use because the change in the register that keep the instruction is the moment where the registers or the memory absorb power. To reduce the number of change between one instruction to the next one, we can use gray code sequencing. We can use a statistical information about which instruction will be followed by which instruction to get the statistical probability of the sequencing of certain instruction. If we have that information, we can design our machine code to have as few bit changes as possible in the general kind of coding. This is only just one of the way to optimize the power that our machine use by manipulating the instruction code.